Hi everyone, today I'm going to be talking about my work on taming resource heterogeneity in distributed machine learning training with dynamic batching. So let's start with the basic question. Why is distributed training important? Well, over the years, more deeper and more complex models have been developed, which have a lot higher computational requirements like ResNet, VGD transformers, etc. And these state-of-the-art models, they train on billions of parameters, which significantly increases the training time. Example, the recent OpenAI's GPT-3 has 175 billion trainable parameters. So what we hope to get out of distributed training is to run the model across multiple servers, which helps us decrease the overall model training time or the convergence time. So let's start with distributed training, talk about distributed training with parameter servers. So here, workers iteratively train on a mini batch of data to compute the updates, which is the gradients, using some optimization technique. That the one that we explore here is a mini batch SGD. And the parameter server are dedicated servers or devices here, which aggregate those gradients from all the individual workers, apply those gradients, aggregate them together, apply them to the weights, and redistributed the updated weights for the next training step. So the caveat here is that training at every step is halted until all the gradient updates from the workers have been received. So this is also known as synchronous or BSP training. Like we can see here in the figure, each worker sends its gradient update from the mini batch of data that it processed. It aggregates those gradients together with some reduce op, usually reduced by mean, updates, applies them to the weights, and send those updated weights for the next training step. And the training continues. So what is heterogeneity basically? Now, in the simplest words, servers with different computational capabilities. For example, if we were talking about a matrix multiplication op, if we do that on an NVIDIA GPU versus an AMD Threadripper versus a Raspberry Pi, you can expect some differences in performance, definitely, for sure. The iteration time on each worker is the time taken to compute gradients on a mini batch. And more capable devices have a lower iteration time compared to the less capable devices, which have more, as you can see in the figure that tries to explain this. If they process the same mini batch, each GPUs do compute the gradients, the major training portion, in a significantly lesser time compared to, say, the Raspberry Pi. But because it's synchronous, the other workers have to wait until the slowest worker completes. So there's the synchronization barrier here, and which is basically training is affected by the slowest worker in the group. So impact of heterogeneity training. We train on 3 workloads: ResNet, CNN, and linear regression. So we try to cover the broad spectrum of different models with different computational requirements. And we ran them on 2 configs, a homogeneous one where every worker in the training cluster had the same computational capability. So here with measuring computational capability as the number of CPU cores allocated. So here a homogeneous system has the same CPU cores allocated, while a heterogeneous system has different CPU cores allocated to each worker. And this for like a 3 worker config. So this is, we compare these 2 configuration and to see like what is the overall increase, if any, in the training time. So heterogeneity increases the training time by 300% for heavier models like ResNet and CNN, while it increases it by 200% for a lighter workload like linear regression. So heterogeneity has an impact, definitely, and not a good one. So how do we minimize the effect of heterogeneity? Well, we somehow equalize the iteration time among the workers. But how do we do that? We assign the mini batch size on the workers proportional to that worker's throughput or the capability to perform some compute. So we measure the throughput as on a CPU as the CPU core counts, while on the GPU we measure it as the floating point operations per second for half precision performance. So what we hope to do is, with different batch sizes, we somehow equalize the iteration time on all the workers, which basically eliminates the impact of that synchronization. So basically, a faster worker should process a higher mini batch, while a slower worker should train on a smaller mini batch. The mini batch size controller. So the mini batch on a worker K is periodically updated on iteration I+1 as this, where VIK was like the initial mini batch size and some change, which is the delta B. So BKI plus 1 is like the updated weight. So we use a proportional controller such that this delta value is equal to the minus of throughput times the error, such that the error is the worker's iteration time minus the cluster's average iteration time. So let me just give you an example by what I mean by that. So like, let's just say for a 2 worker cluster, if T1 and T2 were the iteration times for worker 1 and worker 2 respectively, the error on worker 1 would be T1 minus the mean of T1 and T2, while for the error for worker 2 would be T2 minus the average of T1 and T2. So this is what the controller basically tries to do, which is figure it out. So each worker starts off with the initial mini batch, which is B1 for worker 1, and it's the worker sends their iteration time and their throughput to the controller, and the controller collects all these values from all the workers and updates the values of each worker for the batch size correspondingly. So if the error is positive, you decrease the mini batch size, because if the error is positive, it means the worker is having a hard time to process that given mini batch size value, so you decrease it. And if the error is negative, it means it's able to compute in a lot less time compared to the rest of the cluster, which is the average of the iteration times. So hence you should just increase the mini batch. So about adding control stability, let me just explain what this is. So due to the stochastic nature of the training process, the worker iteration times don't converge. So we see oscillations in the updates. So here's an example here for a 3 worker cluster with 9, 12, and 18 CPU cores. And you see after, the adjustments that happens after every 1K step. So there are oscillations in there. So to handle these oscillations, we add control stability, which is basically don't update the mini batch if it's less than some delta B value, which this is also known as dead banding. Then use exponentially weighted moving average for computing error in the iteration times and enforcing upper and lower batch bounds. So this is basically the flow: compute the iteration time, compute the smoother time, exponentially smoother time error, apply the mini batch bounds, and apply dead banding. So this ensures that our batch size updates stay in check and they don't just go about oscillating. The implementation. So this controller is implemented as part of our OmniML framework, which is built on TensorFlow, and TensorFlow estimated in approximately 2,000 lines of code. After every mini batch update, you kill the training process and restart it with the updated weight. So it's kind of like warm starting training. And I also want to talk about some mini batch HGD modifications that we make. So for K workers, the weights are updated as this, where K is the number of workers, eta is the step size of the learning rate, V is the mini batch size, and F is the loss function. So since we're processing different mini batches on the workers, and conventional distributed training just aggregates, does a reduce by mean, we do a gradient scaling, which in the simplest words, it's nothing but weighted average. So we specify a lambda K for each worker, such that it's basically the ratio of the batch size of that worker versus the global batch size, like the cumulative batch size across the cluster. And we scale the gradient by that value, and we apply that to the weight updates. So this is our gradient scaling. Evaluation. So we test on 3 workloads. So we try to cover a spectrum here for different computational complexities. And we have ResNet running Sapphire 10 image classification, which is like 50K training images and 10K test images on 10 classes of labels, and a single layer CNN on MNIST data, and a linear regression problem on Harvard bar crawl dataset. We test this on our local cluster setup, which consists of workers with 48 core Intel Xeon Platinum CPUs, 256 gigs of RAMs, and an NVIDIA Tesla P100. We also run it on the Google Cloud using E2, N1, N2 machines, NVIDIA T4, P4, P100, and V100. So this is our workloads and the test framework. Iteration times with mini batch adjustment. So since we equalize iteration times by adjusting the mini batches, You want to see like how does it actually fare against the conventional distributed training where you just run the same mini batch on all the workers. So we test this on a 3-worker config with 11, 4, and 24 CPU cores. So it's decently heterogeneous. So this is the training time, iteration time distribution of the 3 workers. So cyan is the 24 core worker, red is the 11 core worker, and black is the 4 core worker. So the 4 core worker is a lot slower than the other 2 workers. And if we adjust the mini batches appropriately according to throughput based, this is the distribution we get. So we are able to equalize the distribution and basically make the iteration time almost same on the workers. So basically the parallel efficiency is improved. Training on heterogeneous CPU clusters. So for CPUs, we define heterogeneity in a cluster as the ratio of the CPU with the max to the min core count. Like for a 9, 12, 18 CPU core config, the H level would be 2. So using these value of heterogeneity levels, we run our workloads across different H levels. So for ResNet, this is what we have. So we saw an improvement of 1.6 to 2.1x when the accuracy threshold was 90% on Cefat 10 for ResNet 50. For one layer CNN, with an accuracy threshold of 99.35%, we saw gains from 2 to 3.5x. And for regression, we saw work gains of 1.2 to 1.5x. So we did significantly better than conventional uniform batching. And training on heterogeneous GPU clusters. So we see what happens when a cluster contains different types of CPU and GPU workers. So for previously how we defined heterogeneity for CPUs, for GPUs we define heterogeneity as the ratio of the flops for different GPUs. So we test this on a 2-worker config using NVIDIA Tesla P100 and a 48-core Intel Xeon CPU. So we train, one worker is a GPU and the other worker is a CPU. And this is the gains that we saw. For ResNet 50, we saw a 4x gain, while for CNN, we saw a 1.2x gain. So here, red is the uniform batching, which is like the same, running the same mini batch on all the workers. Variable batching is the throughput approximated mini batch adjusted training. And dynamic is like in different periodically, we just check, we check the resource requirements and we computed the error and applied the dead bandings and updated the mini batch sizes accordingly. So ResNet improved by 4x and CNN improves by 1.2x in the GPU CPU mix. And what happens when a cluster contains different types of GPU workers only? So we test a 4-node config that consists of 2 Tesla T4s and 2 Tesla P4s. And we saw gains of 4.5 and 2.1x. So pretty decent. So about the related work. So what we came across, that the past work treats heterogeneity as a stochastic performance variation that includes adjusting learning rate proportional to the staleness in asynchronous worker updates, which is a dynamic SGD and constant SGD in SIGBA 2017. Then workers computing gradients in a bounded time, then aggregate whatever results they were able to process, which is anytime mini batch in ICLR 2019, and heterogeneity aware gradient coding scheme to handle stragglers in decentralized non-parameter server setting, presented at ICGCS 2019. So to conclude, heterogeneity is a problem that adversely affects distributed training convergence time, and we implemented a proportional controller to equalize the iteration time among the workers based on the throughput, which was basically adjusting the mini batches on the workers individually. So this is our part of our based on our part of our OmniML framework, which is available at the following link. Feel free to check it out. And the results: ResNet improves on CPU by 2x, while CNN improves by 3.5x in heterogeneous systems. In a CPU GPU mix, ResNet improves by 4x, and in multiple GPUs, ResNet improves by 4.5x. Thank you.